Hi, welcome to Beginning Engineers. Today I'm going to be talking about the chi-squared test. Is there an unexpected difference in these things? What does a chi-squared test do? And it is chi, not chi. Kind of similar to frats, you pronounce it chi. Chi-squared test is a tool primarily used to see if there is a difference between things. It determines a goodness of fit. So you observe something, record the data, and see how well that matches what you expected. How well does your observation fit with your expectations? The idea may not be as common as the ideas of normal distribution or exponential distributions, but you'll see it is very similar and even comes from normal distribution. It helps test if there is a significant difference between two categorical variables. So of course, when you get a sample of something, it may differ some. There is a normal distribution to things, so there will be some difference. But what if there is a significant difference? That's what matters. And chi-squared tests deal with categorical variables. So categorical means the values don't have numeric measures of value. They're not metric values. Things like height or velocity, those have specific measures. You're 67 inches tall. You're traveling at 400 kilometers per hour. Categorical variables are just things like quantities. I have 27 blue marbles. There are 9 people in the room. The bigger the chi-square value, the more the actual differs from the expected. This typically means there's some sort of association. Think about it. If things aren't randomly distributed as expected, then what's the pattern? What's the skew? If things are just totally random, they'll follow a normal distribution. That's what we are measuring for. If what you actually measure is super different than what you expect, something is not normally distributed about your data. There should be some sort of relationship. Before we do an example to learn how the chi-squared test works, let's talk briefly about where it comes from. The chi-squared test comes from something called the chi-squared distribution, which is in turn a squaring of the normal distribution, at least in the most simple version. So chi-squared is all about testing a hypothesis. Does my observation fit what I expect? As you increase your sample size, your sample distribution will begin to resemble normal distribution. This is known as central limit theorem. That chart there is an example of the chi-squared distribution. There's a few charts for it, I just wanted to focus on this one very briefly before doing an example. If you remember from my normal distribution video, you have your bell curve, and everything under it represents 100% of your possible outcomes. It's the same idea with this chart in the bottom left. Each line, eventually, when it goes all the way to the right, goes to 1 on the y-axis. That means 100% of everything that could happen eventually falls under that line. Each line represents a different k, which is degrees of freedom. That's the squares being added together. It's like a sample size. It's the number of total outcomes you have minus 1. X on the chart is the squared deviates away from the mean. It's like the z-score, only it's that z-score value squared. You square it to always keep it positive because it's a distance, similar to normal distribution and standard deviations. F of x is the area under the normal distribution curve. So the whole point of this graph is just to show that as you increase your square deviates away from the mean, you're going to capture more and more of all the possible outcomes. For example, if you look at the topmost line, at a value of x equals 4, it captures nearly 100% of your possible outcomes. What's the square root of 4? 2. So think back to your normal distribution. If you're 2 deviates away, if you're 2 standard deviations away from the mean in normal distribution, you're capturing around 95% of all possible outcomes. Just like the value on that top line, everything underneath it is about 95%. So if you remember anything from this chi-squared, just remember it's like normal distribution. It's all about how probable is the value I'm getting. That's the biggest takeaway from this. Okay, let's look at some chi-squared values and then the probabilities associated with them, so you can begin to get a feel for how likely are certain outcomes. Now the degrees of freedom is how many possible outcomes there are, minus 1. When you're doing things like z-scores, you're typically just looking at one item and comparing it to your sample. But with chi-squared, you can have maybe 7 different outcomes. So that's going to change what a good and bad chi-squared value is. Or what a probable and improbable chi-squared value is. So let's look at this chi-squared table. You'll notice that in all the cells from left to right under your x-squared value header, that's your chi-squared value, they increase from left to right. And that is true for every row. So even if your degrees of freedom changes from left to right, your chi-squared value increases. Now, on the very bottom row, your p-value, the probability that this would occur, you'll notice those decrease. So the relationship here is the higher your chi-squared value, the less likely it is to occur. The less likely that whatever you're looking at fits your expectation. If you get a really high chi-squared value, that means your observation was nothing like what you expected, and the probability of that is very low. We'll touch back on that table later, but right now let's do a quick and easy example to make sense of a chi-squared value. Suppose that you have a bag of 30 lollipops, and you know that the lollipops are either red, blue, or green, but you don't know the quantity of each in the bag. But let's suppose you assume that there are an equal amount of each color lollipop in the bag. This will be our null hypothesis. And this is a typical assumption when doing chi-squared analysis. You assume things are equally split. But you find that when you dump the bag out, you have 12 red, 13 blue, and 5 green. So how does this compare to your expectations of 10 each? So what would the chi-squared value be for this? Assuming that the null hypothesis, our assumption, our expectation, was that there were 10 each. 30 total, 3 options for each. Well, here's the chi-squared formula. It's your observed value minus what you expected for that, then you square that because again, we're looking for a distance away. And we want it to be positive or else things will cancel out. Then we divide that by what we expected. Notice how this is essentially a calculation of the standard deviation. It's a very similar idea. So we do that for each of our options. How different was red than we expected? How different was blue than we expected? How different was green than we expected? We had these expectations for all the lollipops. Now let's see, based on each value, how different things were total. So that's kind of the big difference from normal distribution. Chi-squared allows you to look at groups of things and see the total difference from what we expected. So our chi-squared value was 3.8. That came from the equation. We have 2 degrees of freedom because there were 3 outcomes, red, blue, and green, but then you subtract 1, so 3 minus 1 is 2. Then we look back to our table earlier. The odds of this happening by chance, just by taking a sample, are between 0.1 and 0.2 using the table. See where we get that from? We looked at the table where our degrees of freedom value was 2. Then we found our score of 3.8 between the cells 3.22 and 4.6. Then we looked down at our p-value probability and saw that it would fall between 0.2 and 0.1. When using a lot of programs, you would get that exact probability, but this is just a general way of looking at it to get an idea. This value is too high to be considered significant. Many studies look for a p-value below 0.1 or 0.05. So where is this used in the real world? What are some practical uses? The chi-squared test allows you to see if multiple values in a sample vary more than expected. So unlike typical z-tests that generally just look at one value in relation to the normal distribution of that sample, you can look at a whole set of measurements, categorical data. Do all these items fit what we would expect? This would be useful to answer questions such as, are consumers in a certain geographic area purchasing more product than those in other areas? Do more tenured employees assemble products quicker than those who don't have as much tenure? Does the new automated mill make the cuts with the same repeatability as the human-operated mills? Any area where you can count things and then compare what you counted to what you expected is a great candidate to perform a chi-squared test and see if what you counted is reasonable or if there is some sort of relationship going on. Thank you so much for watching this video. I personally never really use chi-squared tests much in engineering. You see them a lot more in marketing, but I think it is such a useful statistical concept that it is good to be aware of. If you like this video, please subscribe. Have a great day.